All right, so hi everyone. So a couple of things. So one, before I introduce the speaker, I just wanted to announce that the TAP travel applications are now open, and so if you are interested in applying for some travel funding, then you should fill out these applications. The deadline is March 9, and here's the code. So let me get out of the way so you can click on it if you want to. Okay, I'm not seeing anyone pulling out their phone. That's fine. You can always if you're interested, you can ask me or honestly any faculty member, and we'll point you in the right direction. So if you're interested, please apply. And then for today, it is my pleasure to introduce Chihway Chang from the University of Chicago, and Chihway has been one of the leaders of survey from photometric survey science now for quite some time. So she received the DOE Early Career Award from all of her work that she's been doing with the ETH and DESC and LSST DESC. So she's actually currently the survey the science group co-chair DES. So she's one of the people responsible for the recent results from DES by 6. And she's also been extremely active in DESC, including as one of the science coordinator conveners for LSST DESC. So she's basically has her hands in all of the survey data that has happened and that is going to happen, and that is what she's going to tell us about today. So welcome.
Thanks, Hideo, for the nice introduction, and thanks for having me here. And I came by Tucson like over the past years, and I'll dot it in my talk, but it's always really nice to come here. And yeah, excited to tell you about some of the things we've been working on. So I'm going to sort of give an overview. I understand this is a kind of theoretical series, but I'm going to sort of give you a motivation of the things we do and how we, based on science questions, went to take data and answer these questions. Mostly in the context of structure. So when I say structure, I mean cosmic structure, and how we use that to constrain cosmology. Okay, so briefly, I'm going to talk about some background just to have everybody on the same page. And then mostly, I'm actually going to spend most of the time talking about DES. So we recently had a big result, but also because I think my student came here and talked about Decade for a long time, or at least for part of the time. So I won't actually spend too much time on it. Let's talk about DES and some of the LSST kind of preparation work going forward. Okay, so just to set the context, for the non-cosmologists in the room, kind of cosmology today is all about testing this model, this lambda CDM model, which is kind of made out of lambda, which is a cosmological constant, and CDM stands for cold dark matter. So sort of the theory goes, we start the universe with a big bang, there's an inflation period, then the CMB happened, and after that, the universe slowly expanded, and at the very recent, like 4 or 5 billion years, the universe expanded faster and faster. So this is kind of a general framework. It has been phenomenally successful given how simple it is. Has a handful of parameters, but fitted basically most of the data that we have collected. Sort of the guiding principle is that we think geometry of the universe, so this kind of grid, how the shape of this grid looks like, is dictated by what is in the universe. So these are the different components of the universe: radiation, matter, curvature, and this energy. So each of these components comes with some scaling of A, which is the sort of the time dependence. With the last one, we don't really know how it works, so we add an additional parameter W, which is the equation of state for that. Okay, so that's sort of the context. This model has been very successful. We fit a lot of things to it, but it's fundamentally problematic because we don't actually understand it deeply. We don't understand what dark matter and dark energy are. We don't even know if this is a constant or it's not. And then there are additional problems of we're not fully understood the kind of initial phase of the universe where observations are hard to get here. Okay, so we have a model, it fits the data, but we don't understand sort of the microphysics of these components. Okay, so in addition, most recently, I say the past 5 to 10 years, there has been multiple kind of funny things that going on in our data that make people pause and think maybe this is a sign that lambda CDM is starting to fill. So what are these different things? These are basically tensions in the data, meaning you can constrain lambda CDM with one data set very well. You can constrain that also very well in this other data set, but when you compare the parameters that you fit out in two data sets, they don't agree. So this famously showed up in H0, the expansion rate of the universe, but also these more recent ones. S8 is what I'm going to talk about a lot today, is kind of the clustering, how much clustering there is in the universe. Most recent results from DESC kind of reveal these two things, which is evolving dark energy and negative neutrino mass. So this is sort of things that are emerging. And I would say we live in an interesting time because this is not possible to emerge unless your data is good enough and that you're able to combine them. So with these things coming up, I think we learned two things. One is that it actually is non-trivial to combine different things. Yes, like practical, you combine the different likelihoods, this and that, but we're working in a very high dimensional space. To actually assess whether two things are in tension or not becomes complicated. Secondly, because you're combining more things, you're more likely to have things that don't fit quite well together. And basically, we're entering that stage where this is happening. And in a sense, it's good. It's exciting. This is what physics is about, right? You test things, they fail, then you come up with new things. It's kind of exciting times, and I think we should embrace it and really look into these discussions. Okay, so most of my talk is going to talk about structures. So this is kind of the bright things that are in this grid, how they become more and more kind of inhomogeneous going from the left to the right. So this like axis is time. So that's going to be what I'm going to talk about. And in this field of large scale structure, this is sort of a lay of the land of different surveys that's going on. So some of you might be familiar of Lee's kind of past data that's taken, that's currently, like we just analyzed DES, but there are other kind of results coming out. These are called stage 3 surveys. So this is basically what has happened in the past 10 years. DESC is kind of oddball. It's like the first stage 4 thing. And we're at an interesting time where all these like new experiments are starting. So Euclid, PFS, Rubin, Spherex, Roman. So like we had a period of time where we had no data coming and we're just analyzing things. We're again re-entering the period where we're basically trying to like having a fire hose of data and trying to analyze them. So that's where we are, and I think that's it's good. It gives us motivation to finish these things up, but it also is very exciting with this new data coming. Okay, so that's sort of the background. Next, I'm going to talk about DES. So for the young people in the room, so DES actually started a long time ago. So 20 years ago is when this first kind of proposal paper happened, but the planning of it happened actually much before that. I actually think, Igoro, you were on the proposal in the first thing that went to DOE. Okay, so this is kind of the 2005 paper that we usually quote for DES. And okay, so here's the proposal, right? So that was a time where nobody knew what dark energy was. It was like turn of the millennium. People discovered these supernova that seems to indicate the universe is expanding faster and faster. So we really wanted to know what dark energy is. So this proposal is, okay, we're going to use a combination of different probes, 4 in particular, to jointly stress test what dark energy is. And to do that, we need to build this instrument called DCAM, this camera, and put it on Blanco. So the proposal was to use galaxy cluster counts, measurement of angular power spectrum, so this is BAO, weak lensing, and type 1A supernova. And really the power of DES and the kind of the original genius of it is that these 4 things contain both structure probes and geometry probes, and jointly they're going to tell us what dark energy is with the same data set without like proposing 4 different things. Okay, so that's what happened. Somebody made a plot. So this is forecast in 2006. And they can see the idea, right? So we add the different probes together. And importantly, I think supernova plays a role in it actually is breaking the geneticity quite a lot compared to the others. BO is not doing much because it's like a photometric survey, and then the cluster and weak lensing are sort of equally good. So 2006, we're pretty sure Wayne made this plot, but we have not. Okay, so in the paper, this is what it looked like, and then they went ahead and built the thing. So the camera got built, it went on to Blanco, and it's an instrument that basically allows these 4 things to happen. To do that, you need a wide component that does clusters, BAO, and weak lensing, and then a time domain component, a deep component that does a supernova. And that's what the survey ends up being. That's these 2. And again, for some of the young people in the field, actually the original proposal was mostly motivated by following up on the SPT clusters. So originally we proposed this to do cluster cosmology, and that was the biggest thing. So that's why the footprint looks kind of like what it looks like. There's the part that covers with SPT, and there's the stripe 82 that gets your photometry right. Okay, so that's that, and then we proposed, like they proposed some other instrument details to get this camera built. Okay, so the thing was built, started taking data over the last 10 years, I would say, is when the science papers came out. So the year 6 result you just saw was built on like this series of phases of surveys. Science verification, 2015, year 1, year 3, and year 6. You can see kind of increasingly more area and more weak lensing galaxies. This is the footprint on the sky, and the map shown is these weak lensing mass maps that, again, people in Eduardo's groups are probably doing, that indicates the dark matter distribution on the sky. Okay. All right, so that's the kind of the static component. And the time domain component, we've been looking for supernova. So this is a cool animation. You can see each of the lit up points is a supernova. And it only lights up occasionally. That's because these fields, these like 4 fields, are not always in our footprint. So when they do light up, they are in our footprint, and when they don't, they are somewhere else. So yeah, so there's a cool kind of illustration of how we collected these 1600 type 1 supernova. Okay, so that data is all taken. Okay, so it was taken like 7 years ago. So 20. Oh, are we not on Zoom? Oh.
There are 6 participants.
Okay, but is the voice not going through or something? Sorry. No worries. There's the chat. Can people hear me? No, it's okay. We hear. Okay, people hear.
Okay, so people
Good.
here.
I think they said they hear.
They're probably.
Sorry about that. No worries. Yeah. Okay, hopefully people hear. Where are we? Okay, so data was taken for 6 years. The survey was actually finished in 2019. Everything that happened after that is just analyzing the data. The data is public, so DR2 is kind of the raw data products that you can get in this website, and it has like 10,000 coad images, 76 single exposures to the depths that we just talked about. So this is a rich data set, right? So you can do cosmology, you can do a lot of other things, and that I would say is one of the main legacies of DES, just the pure data set. Okay, so you can do something more cosmology centric to have these value added products. So for example, the weak lensing shape catalog is going to contain many galaxies, and then these different items like BAO samples that are clean and have good redshifts. These are 16 million galaxies, 20,000 optically selected clusters. You can cross match to other things, and then the supernova we just talked about. Okay, so as I said, these are all like data products that are going to be public, if not already public, and people can do a lot of things with it. And really, just drill into this message, the biggest advantage here is that all these things are taken with the same instrument, so the calibration is consistent, and that we know from many other experiments can be a problem. Yeah, so we think that that is kind of the true benefit of using DES data. There has been a lot of papers going out, many from this room, and then there are obviously more counting. Okay, so I said in the beginning, DES was proposed to do these 4 things. So where are those 4 things? So this is the status. Since 2024, we've been sort of rolling out the final results of each of these probes. They're not fully finished, but they're almost finished. So BAO 2024, we released, this is a 2.1% measurement of a single point BAO. So that's out. Type 1a supernova, we published something at 2024. So this is like the first cosmology analysis from this full data set. But there was a reanalysis like this last year that redid the calibration from low to high redshift and shifted the contours a bit. But that we consider also done. 3x2.1 I'm going to talk about today is this galaxy clustering plus weak lensing. Was just out a month ago. So that's out. And then the galaxy cluster count analysis, because it requires this sample to be fixed, so it will come out later, hopefully this year, but we'll see, I guess. This thing that was just out, there was a webinar. I think many of you called in probably, but if you are still interested and want to watch the recording, it's here. I put this here because I think our website is a little broken, but this thing will work if you want to look. Okay. I'm going to talk about this, and I will highlight some of the people at Chicago that have been working on now or previously at Chicago that have been really involved in 3x2 point. Judy was a former postdoc, Julia was a former postdoc, Chunhao is a current postdoc, and Daya is a current student. Okay, so just quickly run you through, again, some of you might be familiar with this, so apologies for that. What is this thing we call 3x2 point? It means 3 2-point functions, but let me explain that more in detail. So what we care about is galaxies, 2 kinds of galaxies. One is these red galaxies. They're supposed to live in dark matter halos and trace the clustering of dark matter. We call them lens galaxies. And then one are these blue galaxies where the shapes of these blue galaxies gets distorted because the light passes by the halos and gets distorted. So these, we call them source galaxies, and then we measure their shapes. So we measure their positions, we measure their shapes, and these are the 2 things we care about. From these 2 samples of galaxies, you can form 3 kinds of 2-point functions. Galaxy with itself, clustering, galaxy cross weak lensing, galaxy cross the blue galaxy, this galaxy lensing, and then if you just cross-correlate the shapes of the blue galaxy, that's called cosmic shift. Okay, so these 3 things are 3 2-point functions. You add them together. We call it 3x2 point. And it basically was developed by like Kath Elizabeth Scott. I don't actually know, but like the people here were heavily involved in the development of the first implementation of this in DES Year 1. It has been proven to be kind of one of the best ways you can do weak lensing analysis to be very robust. And then I will emphasize that a bit later. Okay, so we're going to call these source galaxies and these lens galaxies. And really the name of the game for the entire analysis is just to find these samples and really characterize them both in their shapes, their positions, and their redshifts. And that's sort of the most of the work. Okay, so this whole analysis turned into like a very messy pipeline. Each of these boxes is a lot of work. So I sort of organized them by task. So you start with the pixel level, making the coads, modeling the PSF, doing the masks. That goes into both the simulations and defining the samples for the source and the lens. And that then goes into kind of characterizing the redshift, measuring the data vector. And that whole thing goes to modeling and inferencing to eventually get to cosmology. So each of these tasks is a team of people doing the work. I quote the paper that is kind of describing each of the steps. Many of these people, as I bolded here, are early career scientists looking for a job. So if you have a job, they're looking for a job. So these people have put in a lot of work making this happen. In total, there is 15 +1 papers that are submitted on the archive or published. The +1 is because I think the cosmic shear paper is supposed to be submitted tomorrow or something, but that's coming. And then there's 3 in this camp that is still under work. Okay, so I'm not going to spend time on every single box, but I'll highlight some of the main advances that we made compared to the previous analyses. Okay, so for the samples, so this is really understanding your source and your lens sample. The main advantage in the source sample is that we're using a new algorithm that better calibrates the steeper data, and we are gaining about 50% more galaxies. So that's good. So here's just like a measure of the amount of kind of information in the galaxies, and it's more. For the lenses, again, for the people who knew about the history, the previous analysis, we had kind of systematics we didn't fully understand in the lenses. So moving on to year 6, since we didn't fully understand it, the only thing we can do is to make sure that the sample is as clean as possible. So there was a lot of work going into sort of removing galaxies that in the color space look weird. And those end up being stars and quasars, and then using your infrared photometry to do further cleaning. So we think this new sample is much cleaner than the previous one. For the redshifts, again, this is a whole kind of industry of work trying to characterize the redshift distribution. Mainly in this new analysis, we have kind of a better handle of within the error bars what is contributing to the uncertainty. So this on the left is for sources, on the right is for lenses. I'll just point out one thing. For the sources, the dominating contribution, this red bar, is just how much spectroscopic or calibration galaxies we have in high redshift. And that continues to be a problem, and it will be a problem for the next generation data where they go deeper and deeper. You can see it's a dominating factor here. It's not too much for lenses, but it will be the same for when we have fainter sources. There's various different kinds of simulations in DES. I'm just highlighting 3 of the main ones. So image simulations. So this is supposed to be data. This is supposed to be simulations. You can see that the stars are in the same position. You can see them. The galaxies are not. But anyway, so this simulation was supposed to be used to characterize blending in the weak lensing shears. And there's been a lot of advances in better PSF modeling and better kind of star modeling in this analysis. This is a mock galaxy catalog. So it's just kind of getting the colors right for galaxies, so we can see if we can recover redshifts correctly in our method. So that's kind of a mock galaxy catalog. And the last one is interesting. It's the source injection, the synthetic source injection catalog, which is that you take the actual data, you inject a real source in there, and then you try to retrieve it using your normal pipeline. So because when I put the object in, I know exactly what it is. When you measure it out, you get an output versus input that effectively characterizes what your whole pipeline is doing to your data. So that was what this is. And then effectively, they're showing that you can reproduce what the data is doing. So the synthetic source injection is indeed picking up what the whole system is doing. Okay, so with all that, the final thing you need to do is to model. Model a data vector, model astrophysics and other things. So in this plot, again, if you're familiar with the modeling game, the main question is where do you remove the scales? So we have these measurements of cosmic shear and galaxy-galaxy lensing and galaxy clustering, but at the very small scale, we don't trust them because we don't know how to model them. So you want to remove enough so that the biases are not dominate in your cosmology. So this is just showing that for everything that we can consider at that point, we are not expecting the astrophysics to bias our results by more than 0.5 sigma in this one. Okay, so finally, blinding was a big thing in DES, meaning we don't want to make analysis choices while looking at the results. So while you see cosmology, if you don't like it, you don't want to cut more data so that it goes to somewhere you like. So blinding means basically that. You don't want to make analysis choices based on what the final data is. In practice, one of the hardest thing to pass for us before unblinding was to make sure all the 3x2 point data vectors are consistent with each other. So that was one of the points we told ourselves we have to pass before we move on. And this is the number. The number is supposed to be greater than 0.01. So you can see in the left row, left column, it's not. Some of them are not. On the right, all of them are. So we made a painful decision of removing a bin because they were not passing this internal consistency test. That in the end didn't actually matter for cosmology, but it was a painful decision because you don't want to, it is a kind of a annoying thing to do, removing one bin and not explaining it well enough. But anyway, that's what happened. We moved on, and then we had a cosmology result. Okay, so I'm going to talk about the kind of highlights of this cosmology paper that came out about a month ago. You can read the details in the paper. But before we go on, let me explain what I'm going to show. So all of the plots will be shown in kind of two parameters. The kind of normally, what we care about in lensing is omega m and sigma 8. Omega n is how much dark matter there is in the universe. Sigma 8 is how much things cluster on the 8 megaparsec scale. And you can see in this plot, if you kind of do cosmic shear, galaxy lensing plus galaxy clustering, and 3x2 point, they have they're generally in this direction, but all tilted by a little bit. And it's this little bit of tilt that allows the kind of the pink constraint to be much tighter than each of them because there is a degeneracy break. Okay, so this plot is a little bit hard to see, so we usually plot it in this way by removing most of this degeneracy direction and defining SA to be that number. It's mostly for convenience. This particular combination is roughly this direction, but not exactly. But it allows us to see more clearly kind of the discrepancies and consistencies between them. Okay, so most of the plots I'm going to show is this plot. Okay, omega m and SA. Okay, so this is our first result. What you want to see is that with the kind of, you take the 3x2 point and you group them into two. One is cosmic shear, which is this one, and one is 2x2 point, sorry, not 2x2, galaxy lensing and galaxy clustering, which is here. So this is formally consistent to the level we care about, which is 0.01 in p-value. So we consider this consistent, and then we can combine them. But things to note, so cosmic shear is mostly constrained in S8, and the other two are mostly consistent omega m. Another reason why combining them is a good idea. Okay, we combine them. So you get the pink. This is a good example showing that in high dimensional space, things don't always go according to intuition, right? So you would think the orange is here, the green is here, they should sit over here. But because of other parameter space are doing other things, when you project here, it is possible that pink actually goes kind of higher compared to the orange and the green. Okay, so the pink is more constraining than individually, and this again highlights the reason why you want to combine them. Yeah, so that's our basically main constraint. These are the numbers. If you care about them, it's about a % constraint on S8. Okay, so I'm gonna flip between these, this to this. Okay, so this is when I add on both the previous DES results in orange and green, and the two renditions of primary CMB. One is Planck, because we always compare with Planck. And this CMB is a combination of Planck 2018, ACT DR6, and SPT DR1. Okay, so this is kind of the more advanced version of CMB primary. Okay, so what do we see? We see that orange to green to pink gets smaller. That's what you want. You got more data, your constraints gets better. Similarly, brown to blue, it gets smaller. You see the things move a little bit in the omega m direction. The SA direction actually didn't change that much. If anything, we move closer to plug. And then for the CMB itself, it mostly stays in place, but kind of shrunk by a factor of 2. Okay, it's easier to see when we look at the 1D direction. So effectively what happened here is that year 3 to year 6 went from green to pink. Okay, so we got tighter and closer to CMB. And then CMB itself also got tighter and closer to like higher values. So basically the two things just like shrunk together and got smaller. So the net result of all of this is that our consistency with CMB actually didn't change. So Y6 to CMB was 1.8 sigma in the full parameter space. And then with Planck, Y3 with Planck is 1.5 sigma. And then if you look at Y6 with Planck, it actually is much more consistent. And you can see it from basically the pink and the brown. Okay, so this is just in case you care about SA tension. This is sort of our layer of the land. This is what we're saying. Okay, the other thing we're very proud of is we finally did a version of what we said we would do 20 years ago, which is combine these 4 things. So this is the first time we've ever combined these 4 things. The pink again is our 3x2 point combined with clusters that turned into brown. And then supernova and BAO only constrain omega m, so it's this like vertical line. So brown plus vertical line gives you orange. So we are no longer only constraining SH here. We are also equally constraining an omega m compared to CMB, and that's, I think, the first time from the same experiment anybody has done that. So we're pretty proud of it. This brown curve has some assumptions in there, and it's not in its final form. So there will be an updated version of this that hopefully makes this orange counter even smaller. That will be the final DES, all dark energy combined results. Okay, I will not be showing WA today because the paper is not out. The plot has been briefly shown in AAS if you care about it, but there are forecasts. So this is kind of forecasts with the most recent 3x2 point and BAO and everything of everything combined in W0WA, also plus CMB in green. I want to compare that with our 2006 prediction, and these should not agree, right? There are many things that went wrong between these 2 things, so they're not equivalent, but magically they actually are very close. So you can try to mentally overlay. I didn't do it because I think it's too subjective. You can try to mentally overlay this red on top of here. It will be basically slightly bigger than the green, and that's understandable because this is DESI and not DES. But it's remarkably close is what I'm trying to say, which is kind of crazy. So we didn't need to build the whole thing and measure the whole thing. Like could have forecasted that in 2006. That's not totally true because this thing, hopefully when we measure, it's not going to be square on in the crosshair. It's probably going to be somewhere else. So yeah, so I think it's a good kind of assurance that we are actually on track, right? We are going to actually produce this forecasted constraint with DES, and that's assuring. Okay, I'm not showing this. I'm not showing W0WA from DES, but if you all were at, some of you were at Convi's talk, I think a few weeks ago, you might have remembered that W0WA is very connected to omega m. So the fact that we have omega m constraints could actually indicate something that we will see in W0WA. So where is this going? So if you remember Tom's talk, or let me summarize it anyway, that if you have systematics on omega m, it is possible like to create a discrepancy between BAO and CMB. It is possible when you fit W0WA, it will have a preference for that. So what we could do as DES is it's providing an independent cross-check of omega m, right? So this thick pink line is everything DES combined, and we are actually pretty consistent with CMB. So if hypothetically you want to say, okay, let's say there is systematics in both BAO and in either BAO or CMB, DES basically adds a point saying we are consistent with CMB. So maybe it's a problem with BAO. But that's like with a lot of assumptions. But this is a kind of interesting point that we could kind of guess what's going to happen with the WNWA results.
Pardon me, a question, if you don't mind. If you could go back a couple of slides. Up, no, go forward.
This one? No.
Yeah, so where you have the DESI results there, but where's the DESI, dynamically varying dark energy? Because the DESI stuff looks like
this
it's
is the forecast. So this is we're centering it on that. So the DESI result is down here.
Oh, okay. I'm sorry. I didn't understand. This is simulated
This
data.
is simulated data.
My apologies.
No. It's confusing. Yeah, I probably should have shows the actual thing, but yeah. Okay. All right. So that's the kind of main DES cosmology results. But DES is a pretty generic data set. We can do many other things. We certainly can do more than these 4 things. So in the next couple of slides, I'm just going to kind of flash some of the other things people do with DES data for cosmology, or for beyond cosmology even. So one thing, again, many people in this room are also working on is to get more information from the same data. So the kind of angle that we're taking here is looking for higher order statistics. So we can measure 2-point functions, but we know that large scale structure is highly non-Gaussian. So it can't be that this is all the information we have. So here's just a collection of efforts trying to look for kind of higher than 2-point information. I'm just highlighting Marco because he put a lot of work in this whole group, and he also worked with kind of people in Arizona. So here are just like some collection of high order statistics, scattering, transfer, moment, wavelets, the CDFs, aperture mass, persistent homology, so what have you. Yeah, again, highlighting people here in this group are also doing field level, so it's kind of way beyond any of this. It's using the entire field, which is another very exciting approach. There are things you can do when you combine DES data with other things. I was just at this KICP, and some of you were too, workshop last week, where the whole workshop was about combining data with data. Here I'm just highlighting combining DES galaxies with CMB lensing from SPT. There's a series of work that was done by Yuki, Eric Baxter, and myself that combined these and performed kind of further cosmological inference. The basic idea is if you put CMB in the back of all these galaxies, which is where it is, it also will get lensed. So it will trace the same large scale structure as these galaxies. So you can consider doing more 2-point correlation functions between these 3 planes in cosmology. This is work done by DES Year 3. There's ongoing work to push that for basically newer data sets. The last angle I think is kind of interesting is sort of towards the angle of understanding astrophysics. So as I said earlier, there is this process in our analysis called scale cuts, where we remove the very small scale information because we don't know how to model it. But you can try to model it still with more parameters that basically is parameterizing astrophysics and not cosmology. So Georgios is one of my former students who basically looked for modeling these small scale data. So this is one bin of a galaxy-galaxy lensing measurement. If you see this very faint blue box, this is the data we use for cosmology. So you can see all the signal to noise, we basically just throw away. And it's because we don't know how to model it, but it also is very, very wasteful, right? This is a lot of signal to noise. So anyway, so he has a few papers looking into modeling it, and you can see the model is very complicated. But anyway, you can model it, and then this plot is showing kind of galaxy, so halo mass to solar mass relations at the different mass scales. So yeah, so I think there's still a lot of work to do here. When we go on to the next generation of surveys, if we don't figure it out, it will be very wasteful because you build the whole LSST and then you basically throw out all the galaxies you additionally measured, and we don't want to be there. So hopefully that's another area. Okay, so I think I spend, when does it end? There's 20 more minutes. Most of the time on DES. Just to summarize this part, and maybe if there's any questions. So DES year 6 cosmology is wrapping up. So far what we're seeing is just with DES, we are consistent with the CMB primary at basically 2 sigma. This is one of the most robust structure probes we can do because a lot of the systematics cancel out. There will be more cosmology to come this year and probably later as well. That hopefully will further kind of enrich the literature of using structure probes to constrain cosmology. We don't like in the DS paper, we're not saying that there is an essay tension. You might want to take the DS result and compare with other things and see if there's enough of the other independent probes that you're gonna believe there is a tension. But I think in the DS paper, that is our stance. For the data products that are coming out of DES, they will all be public, and we think there's a lot more science that can be done with it. 3x2 point is just like the first thing that you can do with it. There's a lot more. So hopefully people will take the data and run with it, and that'll be exciting. Okay, let me pause and see if there's questions immediately before we move on to something else. Okay, everything clear? Yes.
About the bin 2 thing.
Yeah.
Would you, I mean, maybe it's.
No, I can, yeah.
I saw you had like the p-values for the different combination subsets of the 3x2, right?
Yeah.
Like, was the problem with the entire bin 2, or is there a particular part of the 3x2 data vector that's problematic? And then just a higher level question, like, was it decided initially that you would just chop off entire bins? And if so, like, is there like a reason to expect that a particular bin?
So
yeah,
it's a whole thing. So we decided before we saw anything that this is our criteria to unblind. That all of these PPD needs to pass. Okay. So we went into the unblinding process, and then that was the first row, and then we saw these numbers basically, right? So and then people start panicking. So there was a lot of things that went on at that point. The smoking gun for bin 2 is that the redshift kind of posterior for that bin was pushing against the prior by a lot. So others are kind of here and there, but that one was really pushing very hard. And that was kind of the reason we kind of focused on that bin. So there was a lot of investigations, like you can make that the redshift uncertainty larger for that bin. You can change the covariance. Like there's a lot of things that was tried. None of them convincingly kind of removed the problem, like meaning none of them convincingly made this number a lot better. So because we couldn't identify what exactly the problem is, taking it away entirely was like a conservative approach, and that you're not saying it is because our redshifts are totally wrong, or like it can be anything that was wrong. It could be like systematics or whatever, the weights or whatever, other things that could be wrong. But by taking it out, we kind of removed that.
the redshifts of the lenses. Is that
Redshift
right?
of the lens.
I see. Okay.
Not the sources.
Yeah.
You asked about something else.
Well, it was all just. I think you answered.
Okay.
I mean, there's various follow-up questions, but
There's various follow-up.
they can.
Okay, so maybe just one more point. And then we went back and said, did we even see this in year 3? And it turns out we did see it in year 3, but it was not constraining enough to be a problem. And then there was sort of a follow-up. So the running hypothesis round now, which we don't have a solid way to fix, is that in DS, and this was explained in the webinar, the DS filters has this gap between the R and the I band or something. And then the oxygen line gets messed up when it goes through it. And that causes that particular bin redshift to be less reliable. Does that mean that going forward we should always remove bin 2? No. I think LSST, first of all, you don't have that gap. But also I don't think that like I don't think we're saying that is all of it. There might be other things that we don't fully understand.
Right, but if that were true, it would mean the entire bin 2 should go, right? There's a reason to get rid of it.
Yeah, yeah. So I think that's just like the most smoking gun reason. We didn't sit down and simulate it and make sure that actually is happening, but that's like sort of where we are at when we remove that bin. Yeah, but it is highly unsatisfying, right? You want to publish a result with all of your bins. So I think it was a pretty painful decision. Another question.
Maybe to just briefly follow up on that. In DESC 3, there was the X-lens parameter,
Yes, we always remove some bins.
which
yeah.
kind of helped to get some flexibility to reconcile psi plus with to cross 2 point.
Yeah,
Is it used here also?
this one we didn't do that particular test because yeah, what does that actually tell us, right? So I think we'll still need to remove it if it like a significant X-lens is affected.
So do you have a significant extent or
I
do you?
think there was none. Yeah, it's a different kind of systematics, I think. I think we're pretty sure they're different kinds of systematics, but we don't know exactly yeah, what is causing it. I think the whole DES experience have told us that we keep saying sources are hard, but actually lenses are pretty hard. And yeah, so there's that. Yeah, the whole DES experiment is kind of the, like, you never know what is hard from the beginning. I think in the beginning we thought we were going to do cluster cosmology and that's it. Nobody ever thought weak lensing is going to work, and then it worked. So there's that. Okay. Okay, so the next two parts, the first one is decade. As I said, I'm just going to quickly blush over it because I think I mentioned most of it. I just want to advertise, we have a shared catalog that is covering these 9,000 square degrees outside of DES, so the teal region. This is born out of a kind of a program to do near field cosmology. So my collaborator, Angelica Wagner, wanted to cover the whole southern sky with DCAM data and to find those brightest dwarfs. But after he took all the data, he was like, maybe we can also do far field cosmology. So we made coads and measures shared and did that. So that's the data, and it's quite a significant chunk that overlaps with a lot of things. So it's turns out to be super useful. We have released our shared catalog, so if you want to access them, they are available. And we're still producing more data products coming from this data set. It's a collaboration of mostly Chicagoland people from UChicago, Argonne, UIUC, and other places. The kind of main reason you want to do that is the following. First, it is a different part of the sky as DES. So this cross-checking of anything that DES is seeing is useful. It is additionally useful because it's basically the same processing as what DES went through. So you can trust that the photometry is probably at the same level of quality. And then the final thing, again, I think that I talked about this, is that the data was never meant to be taken for cosmology. So there's depth variation and there's other things that are slightly non-ideal. But as we showed that you can actually do cosmology with it, and that has implications for like LSST and whatever the next survey is, that the data you thought that was not good enough may actually be okay. And I think, yeah, heading into LSST, that's a good lesson because we know the data quality is maybe not as good as we thought, but perhaps it's okay. We can still do cosmology. And then again, highlighting this Thayas, phenomenal grad student, he did most of the work. Most of the work meaning these 4 papers and more. So these are the 4 papers that describe the catalog, the redshift, the modeling, and the cosmology in this data set. And then the last paper, combines it with DES to constrain cosmology. And the total thing is 13K square degrees of the sky, which coincidentally is how big LSST is going to be for the first year. So a lot of things we're doing here also perhaps is a kind of a precursor or a test for LSST. Okay, so cosmology, the yellow contour, it's like 3 times tighter than the DES year 3, as we expect. If you care about S8, it's very long. So yeah, so I think mostly the plot is just to show that you can do cosmology with the data. It's not crazy. So that's that. Okay, so we have processed, vetted, and released this catalog. And then we showed that perhaps the slightly suboptimal data is still good for cosmology. Or at least if you relax the criteria, you can get more data to do cosmology, which is good. Okay, in the final 2 minutes, let me quickly talk about LSST. So this is the survey that is supposed to start anytime now. You all live very close to NORA Lab, so you maybe are following what's going on more than I do. But my understanding is going to happen very soon. Okay, so LSST is a long time coming. People, if you know me, I did my PhD on LSST. The first time I came to Tucson, I took a study grade LSST CCD chip. I took it up to Kip Peak. I put it in a telescope that does not exist anymore. But that was the first time I've been to Tucson. So since then, many things happened. They broke the ground, they built the things, and fast forward. Then 16, we started to build the thing. You can see like the rough structure of the kind of artist rendition of LSST showing up. That's the dome. It's a giant like monster. If you see other things to scale, I think there's a close up of like a person to scale. It's like a monstrous thing. I think my telescope got moved to the mountain top. Okay, that was a telescope that went in. And this is kind of the dome fully covered. You can see people. So this movie ends in November 2022, where the kind of the outside of the telescope mostly was done. The rest of it, of course, you all know, is kind of shipping the camera over there, polishing the mirrors and all that stuff. And commissioning has been going on for a while. So here are just some pictures. This is fitting the camera into a very tight-knit mount. This is first light. I think it was June last year. And since then, it's been on commissioning mode with various different programs running. This is a timeline that I got this last week. I hopefully it didn't change since then. But it is real-time updated. If you go to this link, it is updated very frequently. Okay, so this is probably what you care about. First light happened last June. There was this data release that happened last June as well that consists of kind of the early ComCam data, commissioning camera data, as well as some LSST data. So people have been playing with this data. And then all eyes are on this start of the LSST. And currently it's slated to this month or next month. There's with an error bar. So sometime this bracket, or maybe it might get delayed for a few months, but it will start. It will start this 10-year journey of taking data. And the next number you care about is data preview 2. So this is later this year, and it's going to release a bunch of data. So the data it's going to release is LIST. So it has about 700 square degrees of wide field and all the deep field data that's going to be released to the world. It's not huge, but it's big enough if you want to kind of play with LSST data. That's a good opportunity. And yeah, depending on when the survey starts, you can count on the later releases to happen. Okay, so I'm going to quickly mention some of the things that people have been doing in my group to prepare for this data, including simulations and stage 3 survey. So one slide each. So baseline, we want to do a 3x2 analysis. You better be able to do it on simulated data. And that's what Judy did. She basically had a mock LSST data and tried to see, even in the cleanest possible case, can we actually use LSST tools to get cosmology? So the answer is yes. It is a very artificial case, but at least in this case, we are ready. Of course, that doesn't mean we were actually ready, but she has like kind of the first go of showing that we have the tools to do this analysis. Like a bit more closer to data, Jasmine Jefferson is a grad student with at Chicago. So she has been looking at existing stage 3 data and asking if we do coherently the same kind of diagnostic tests, do we get reasonable things? This is very technical, but these plots are showing kind of correlations of PSF shapes and sizes and the errors. This was a fun exercise, mostly to understand the psychology of the different collaborations, where people decide to cut their samples, where people choose to use their data. So that was a fun experiment. And Trehan is a grad student at Chicago. He is interested in looking at spatially varying systematics. So here are maps of different things, extinction, zero density, whatever, and how these things imprint into our shear and whether that matters for LSST. So he mostly been playing with kind of PCAs and how to model how these properties propagate into shear. And finally, Ashe, grad student at Chicago, he is actually touching Rubin data. So he is on the commissioning team and looking specifically at how chromatic PSFs could affect our shear measurements. This plot is not super meaningful, but just saying this plot looks a lot like this plot, and that LSST data looks a lot like DES data. So that's assuring, meaning like there's nothing too surprising, and yeah, we can use the same modeling techniques to do Rubin data. Okay, so that's kind of just a quick show of things that are happening. Just to wrap up the Rubin part, Rubin survey is about to start. I've been saying this for a long time, but it's really about to start. And it's a long time coming. I've been waiting it my entire career. We're working with various different things to make sure we're ready when this data drops. For sure, we will still not be ready, but at least we would have anticipated our unreadiness. So we're all kind of excited for the data to come. Okay, so let me summarize. I am just on time. So I talked about 3 things. I talked about DES, how we did the final result. We made various improvements. So first is that we have the 3x2 point lambda-CDF results. And second is that we did the first time combining all 4 probes as we were promising 20 years ago. And that's cool. I talked about decade very quickly. We have this new data set that covers an LSST-like footprint. And then we showed that with suboptimal data, you can still do cosmology. And finally, for LSST, I guess we're just ramping up with various different venues to try to get ourselves ready. Sorry, I don't really know why I have an alarm there. But yeah, so that's sort of what's happening with our group. Yeah, I'll stop here and take any questions further.
There's already been some questions, but would anybody like to add more questions?
So that's an awful lot of hard work and everything with DES, but I'm wondering about DESI. How does DES work with the dynamical dark energy that DESI claims to see? Does it, agree with it, disagree with it? Does it enhance it?
Right, so, okay, a couple of things. So the DESI result, the most significant one was combining DESI BAO, DES year 5 supernova, and CMB. So for BAO and supernova, these are geometry probes that they kind of work in a similar parameter space. the DES results will be significant in the following way. It is a structure probe. It's kind of looking at different things. So it will add to it, not very significantly, arguably, but it will add to it the same way CMB adds to the picture. So if you remember how the DESI counter looks like, DESI on itself doesn't detect evolving dark energy. It has to be added to something else. You can add to CMB, that gives you 3 sigma. You can add it to supernova, that gives you 4 sigma. So DES can come in and kind of replace the CMB bit because we're doing similar things. So I think that is where the DES results will come in. Does that make sense?
Well, say will come in or have come in. I mean,
No.
is work to be done or work that has been done.
So it has unblinded. We just haven't published the paper. But yes, it will do the thing I said it will do. Okay. Yeah, the plots was shown in somewhere else, but it basically is replacing the CMB and shifting things a little bit in that direction. So I think the significance of that is that then it is a low redshift only measurement, right? If CMB is out of the picture, then it's just DS supernova BAO and DESI BAO. So it's sort of saying something different in a sense.
More questions?
Yeah, so thank you very much. And so you mentioned that there's various modeling challenges that still need to be addressed, but I feel like DS has done an amazing effort in pushing the state of the art for LSST. And let's say for a young grad student, where do you think that like the most benefit can be gained, and where do you think that the community maybe is kind of slightly not pushing as hard as it should?
I mean, I think it is probably not. I think people would agree that currently the limiting systematic is mostly astrophysical. So intrinsic alignment and like galaxy bias and like small scale virion like things. So, and there's been a lot of work doing cross correlation effect countries. I think one of the important things is the community needs to come together and agree on something. So like the baryon problem, I think there's been a lot of measurements, but I don't think people are converging. So I think once that, because if you don't converge, then for LSST, we're still going to throw away all the scale and still use this. I don't know if that's for a young grad student, but I think that's one area that that people should work on. The other area I think is not entirely solved is blending. So I think every time we go deeper in our data, weird things happen. And for year 3 to year 6, we didn't get wider, but we went deeper, and then blending became a more important problem. So that is a wide, like, that's not just shapes, right? That's photometry, that's a lot of things. So that is, we know it's going to be a problem. We know all LSST data, galaxies are going to be blended. And I don't think that's a figured out problem. Again, not sure if it's for a new grad student because that's a really hard problem, but I think that area is unsolved. I don't think what we're good. Yeah.
So just running meta detection is not enough to.
That doesn't account for the redshift dependent one, and that doesn't that also propagates to other things. That propagates to redshift that I don't think we are fully account. Oh, partially, but yeah, I think that area is unsolved.
Yeah, thanks a lot for your talk. Actually, are there any current like plans for legacy survey, like for DES? And if there are, like, for example, what people would have in their mind about the improvement? Like, are there?
What do you mean legacy survey? Actually,
I'm just like having something in my mind, like similar to what KICS has done. It's like they
just call it legacy though.
Yeah, but it's like they greatly modify some component of their pipeline, which they were not satisfied with, or they think like there were some defects And
Do you
then
mean like the redshift?
the
thing?
redshift calibration. So I'm wondering like if there are something similar for DESC. Like,
I thought Kids Legacy was just their final result. They call it Legacy. Yes, they did modify their redshift, but I'm not sure that's why they call it Legacy. For DES, yes, I'm sure somebody will come and reanalyze this for sure. Yeah, it would be nice if somebody figured out what bin 2 is doing. That would be nice. Yeah, so I like this is the first one, definitely not the last one. I think it is our expectation that people reanalyze this for a long, because like LSSU is not going to be ready for a long time. So this is still the best data set out there to do a lot of these experiments, and I think people should do that. Yeah, but DS internally, no, we're all, yeah, we don't have funding anymore. We're not doing anything. We're just all kind of dispersing at this point. But yeah.
All right, so let's thank Chihway one more time.